So this short video will introduce the concept of colligative properties. We're going to assume that our solvent is water, although you can have colligative properties in other solvents as well. We're going to assume that our solvent is exclusively water. So our colligative properties are going to be fine-tuned properties that depend on the collection of material solute particles, chemicals in water as a solvent. There are four colligative properties that typically we are concerned with in an introductory chemistry class. It doesn't really matter what order you look at them in. It's not as if there is colligative property number one, what have you. But the way I have them here is logical. When they're presented, you'll see the logic behind the ordering here. So we're going to start off by looking at vapor pressure lowering. That will then produce the phenomenon of freezing point depression and boiling point elevation. And then we'll give a couple of examples of osmosis, and we'll contrast that with dialysis, which is often referred to as reverse osmosis. So that'll be our procedure. But first of all, let's have a look at vapor pressure lowering. Okay, so I've cleaned up the board and I've plotted a graph of pressure versus temperature, and we're going to use this to explore vapor pressure lowering. So this is water as essentially a phase diagram for water. So I'm going to write over here phase diagram for water. So any solvent can have its own phase diagram, any material for that matter can have its own phase diagram. We're interested in the phase diagram for water here because that's the solvent that we're going to use in this introductory level overview of colligative properties. So when we plot pressure against temperature, water has a unique shape in that there's a slight how do you describe that? Not quite parabolic, but definitely a rising slope as you go up until you get to this point here where it branches off. The point where it branches off is where essentially three lines meet. This is called the triple point. So I'm going to call that T, where T is the triple point. Maybe we should call it lowercase t so as not to get confused with uppercase T, which is temperature. And the part of the graph that's on the left, that's kind of blocked off here on the left, this is our solid phase. So anything with the pressure and temperature needed to get inside this part of the graph would be a solid. Here, this almost wishbone looking part of the graph here, or the V shape here, this would be a liquid part of the graph, and anything to the right here would be the gas part of the graph. So as you can see, it's a phase diagram because we have the three major phases, solid, liquid, and gas. And the triple point is where essentially an infinitesimal change in pressure or temperature could inch you as a solid, inch you into the liquid region, or inch you into the gaseous region. This part up here, I'm going to call it lowercase c. C is the critical point. And this region up here is very interesting. It's not really of interest to us at this introductory level. This is the supercritical fluid region. Which is a whole other phase of matter that is beyond the purview of this introductory chemistry class. So we won't worry about it, but it's neither a solid, liquid, or a gas. It's something else, and although very interesting in its own right, it's just not the purview of today's discussion. Okay, so we've outlined the graph. So let's add some features to this graph. I'm going to go ahead and add some red lines. and then I'll annotate what the red lines are supposed to mean. So I've brought in a horizontal line going right across here, and then I've dropped two vertical lines down here. If this were exactly 1 and the units were atmosphere, so we've got pressure in units of atmosphere, then at 1 atmospheric pressure, the temperature at which water goes from the solid to the liquid phase, or starts that phase transition, that would be the freezing point, and that would be at 0, where we've got temperature in degrees Celsius. So the freezing point of water, when water goes from the solid phase to the liquid phase, would occur at 0 degrees Celsius. If we continue into the liquid range now, at 1 atmospheric pressure, the temperature at which the liquid phase transitions to the gaseous phase, that would be at 100, and that would be the boiling point of water. So just as to orient us to how we would use this diagram. Okay, so we're interested in vapor pressure lowering as a colligative property. So that is a reduction in vapor pressure, which I'm going to signify by this small arrow here. So my vapor pressure lowering, I've dropped it down vertically on my y-axis, so from this value of pressure down to here. Now I'm going to draw a parallel line to the original black curve here, but moved by a distance of my vapor pressure lowering. So this is going to be tricky to get it to look neat. But essentially I've drawn a parallel line reduced down by the amount of my vapor pressure lowering. And I'm also going to draw a line parallel to this black line. Again, reduced down by an amount of quantity proportional to this vapor pressure lowering. So a consequence of this initial vapor pressure lowering is that it extends the liquid range. So to contrast now, I'll use a black marker to look at these 2 points here. A consequence of this extended liquid range is I now have a new freezing point. How do I know it's new? Well, it's now the boundary of my solid liquid range. So at this lower temperature, so my temperature is now decreased. The lower temperature, the new freezing point, is now less than 0 degrees Celsius. And likewise, I've now extended my liquid range on both boundaries, so I've now got a brand new boiling point, which is now greater than 100 degrees. So I've elevated my boiling point. So the vapor pressure lowering has led to the consequence of liquid range, an expansion of the liquid range, the temperature expansion of the liquid range, to now lower temperatures of phase transition and higher temperatures of phase transition. So I've effectively lowered my freezing point and elevated my boiling point. So what does this mean? Well, this means that if you are able to lower the vapor pressure, which would then cause this freezing point depression, let's say you had your sample, let's say a sample of ice at 0 degrees Celsius, then under these conditions, that sample of ice would appear to melt, not because heat is being added to it, but because you're shifting the goalpost of where the phase transition occurs. So now you would enter, if you were initially in the solid phase here, because you were anywhere in this region here, the boundary is moved. You've not moved, but the boundary is moved. So now you'd be in the liquid range again. And this is exactly the phenomenon of how when you add salt to an icy road, the salt would appear to melt, although you don't see a temperature change. Again, it's not the temperature that's changing, it's the boundary at which the two phases meet, the liquid and the solid phase, that's moving because of this colligative property. So in my opinion, the freezing point depression, which again is, so essentially on this board we have 3 of our 4 colligative properties: the vapor pressure lowering, the freezing point depression, the boiling point elevation. We can see that these 2 are a manifestation, causality of this one, or sorry, caused by this one. This is a multi-billion dollar industry. So in the US alone, I think these figures might be about 6 years old, but off the top of my head, I roughly think about $5 billion is spent. I think that's about right. Order of magnitude, billions of dollars are spent on salt in roads. But it can lead to $1 trillion infrastructure problem, because when you salt the roads to make driving conditions safe, you effectively corrode the bridges and the infrastructure and the rebar in the construction of the freeways. And if you drive around any metropolitan area in the US nowadays, and in any country for that matter, you'll see rust coming out the concrete in the bridges, especially in states or metro areas where they salt the roads heavily. So, and to renovate that infrastructure would cost trillions of dollars. So we have a multi-billion-dollar industry causing $1 trillion fix-me-up down the road. So it's very important that students learn about colligative properties beyond passing an exam, because it's a real civic issue. It's a real issue that the economy everywhere is going to face. And there's some real opportunities for innovation beyond salt and roads. Okay, so I think we've exhausted this board as much as we can. I'll pause the video and then we'll spend a few minutes trying to understand how the vapor pressure lowers to begin with. So we'll continue now to look and try and answer the question of why is the vapor pressure lowering to begin with. So here I've outlined the solid phase for water, and we can see that here these spheres represent water molecules, and I've represented a regular array of spheres to represent the orderly structure of the solid phase. Here we've got a slightly less ordered structure, so I've changed the location of some of the spheres to represent that lack of organization. Here I've got water aqueous, so just to point out that S means solid, L means liquid, AQ means aqueous. So that means it's water dissolved in water. Or rather, there's something dissolved in water. So here it's essentially being contaminated with something that I've colored red. The contaminant could be salt, it could be sugar, it just has to be something that's not water. So let's say it's some kind of contaminated water solution, and I've indicated aqueous to represent the fact that there's something that's not quite pure about it. And then the gaseous phase of pure water, I've represented here. There's large separations between the molecules. The arrows represent motion and velocity in certain directions, random directions. Okay, so let's imagine we are going to go from the pure liquid state to the gaseous state. So I'm drawing an arrow from the pure liquid state here of water to the pure gaseous state. Now to go from the liquid to the gas is a lot more chaotic, a lot more disorganized. It has more degrees of freedom. If you had to describe this state, you'd need a lot more information. So I'm just going to write low order or lower order, and I'm going to write higher order here. So essentially there's a decrease in order, the order of the molecules, the organization of the material as you go from the solid to the liquid, and then ultimately, as far as we're interested in, from the liquid to the gas. I've placed the contaminated liquid between the liquid and the gas and nowhere else. And assuming I've done that correctly, notice I have a much shorter distance to travel from the contaminated level, which is here, than I had to do from the uncontaminated level. So although there is an increase in order, the increase in order is less. So I'm going to write the change in order is therefore lower, whereas here the change in order was higher. Higher because there's just along the line, let's say the line length represents a numerical value. Here lower because the line shorter represents a numerical value. Okay, there's a fundamental law of the universe that's not really purview of this discussion, but for the interested listener, it's called the second law of thermodynamics. And essentially, that law says that things that happen in the universe are favored if they increase something called entropy, and entropy just so happens to be inversely proportional to order. So in short, for our purposes, there's a law of the universe that says things that decrease order, things that go from a high to a low order, are favored and therefore are promoted, are likely to occur more. So the universe favors, essentially, the universe is going to favor this general increase from high to low order. And it's going to favor the pure liquid more because it offers more, a greater change in order. So both of these processes are favored. The more order you can change by, reduce, go from high to low, but the change is larger, that's favored even more. So I will say occurs more. And I will say occurs less. Okay. So occurs less because it offers something less favorable. Occurs more because it offers something more favorable. And let's see what's actually happening here. What is it that's occurring more and less? What's occurring more or less, regardless of which one of these you're looking at, is formation of the gas. So once you form the gas, you register a pressure. So if I'm occurring less and what I'm doing is making a gas, I'm producing less gas in the case of the red arrow here. So less gas means lower pressure. Versus the more favorable black arrow here occurs more, and that would give you a greater pressure since it occurs more, or since there's more gas. Okay, so occurs more, greater pressure because there's more gas, occurs less, lower pressure because there's less gas. So in short, I take a pure liquid, water in this case, I contaminate it with something that's not water. It results in a more disorganized material, which then has less change in order to form the gas, is therefore favored less, occurs less, manifests a lower pressure, and so we've gone from a greater pressure in the black representation with no contamination to a lower pressure in the red representation. So we've effectively got a vapor pressure reduction. So this explains the origin of that vapor pressure reduction. So now we're going to continue our discussion of colligative properties to look at the fourth and final member of the colligative property family for this video, and that's osmosis. Osmosis is involved with the motion of solvent molecules, and any solution is a mixture of a solvent and a solute, or many solvents and a solute. And the only distinguishing factor between a solvent and a solute is that the solvent is the material that's in the largest abundance, and everything that's in less than the largest abundance is a solute. Okay, so consider a chamber, and let's say this chamber has a separation. So it's got some kind of separation with holes in it. And let's say we've got water molecules. So these spheres represent water molecules. And let's say the water molecules are free to go through the separation in the barrier. So the water molecules on the left can go to the right, and the water molecules on the right can go to the left. Okay, so they're both the same. Let's now say we add a material that's not water in the far corner of just one of these containers. So now this container is different. So let's say this red object, it doesn't matter what it is, it just can't be water. So let's say it's solute. Solute because it's in a lower abundance than the solvent. So let's say our solvent, which I'm just going to assume is water, and then both of these are forming or potentially can form a solution. Right. Okay. So essentially osmosis is now invoked. I've got the motion of solvent. I'm going to induce an osmotic pressure, which is going to make these solvent molecules move towards the solute. So I'm going to invoke an osmotic pressure pi. So pi, the Greek letter pi, this is my osmotic pressure. So this is how I'd represent the motion of the solvent molecules. Okay, so why are they doing that? Well, I've generated a gradient. So why pi? The answer is because the solute generates a concentration gradient. Concentration is not that important. The important word is gradient. We know from Newton that forces act on gradients. Forces act on gradients. It doesn't matter what type of gradient they are. It could be a concentration gradient. It can be any type of gradient. So let's just use a visual to try and understand what's happening here. A gradient just means a difference in ends. So here I've got a high gradient, or a high end, and here I've got a low end. So my high end and my low end, and essentially if I were to put a test object here, let's say a marble, let's say this was just a ramp, my gradient, I know that because of the force of gravitation, the test object would roll down the hill. If I made this ramp completely flat, there'd be no gradient anymore, there'd be no force to act, no net force at least, so the test object wouldn't move. So how can I use this visual, basic visual, to understand this osmotic pressure? Well, I've put a variable here, which has now induced a high osmotic pressure, and a low pi. I've now got a pi differential. So the solvent molecules will move to try and lower the pressure that's being generated by the presence of the solute. And once the high, so here obviously the test object now is not a marble, it's just a solvent molecule. So as the solvent molecules move, they lower the pressure that they had over here, and they increase the pressure over here, so they take away the gradient again. So eventually what will happen is this contaminant here will eventually dissolve, and it will redistribute throughout the entire container. And once again, both sides of the container will be the same. So eventually, both sides of the container will be the same, so both sides of my gradient will be the same. So I'm just going to write same pressure, and if I were to put a test object here, there'd be no net motion anywhere, so there's no pressure differential, so there's no apparent osmosis. Okay, so this is a quick look at osmosis at an introductory level, and most people have heard this word because this is how a lot of bottled water can be purified through osmosis or reverse osmosis. The equation for osmosis is pretty straightforward. It involves the motion of solvent molecules down a pi gradient or a pressure gradient, where pi is equal to I, capital M, capital R, capital T. So this equation, if you've already studied gases, this equation should look pretty familiar, pending a couple of interpretational leaps. So first of all, I is just the Van 't Hoff factor. So remember, colligative properties typically have a Van 't Hoff factor. I is just the number of, well, for our purposes, I is just the number in the collection. So for example, a covalent compound would have a Van 't Hoff factor of 1. An ionic compound would have a Van 't Hoff factor depending on its solubility. So if it was completely soluble, the Van 't Hoff factor would just be the sum of all the pieces upon dissolution. It can be a fraction thereof if it's only partially soluble. But we'll consider Van 't Hoff factors that are either 1 or that relate to ionic compounds that are completely soluble. Okay, so just you typically have this if you have a colligative property. M is concentration. And specifically, the way it's written here, it's molarity. Now, molarity is moles per liter. So we can rewrite this as pi is I moles, which will give the symbol N. So typically N is moles. So we have N, and then liter. Well, liter could be volume. Well, liter is a unit of volume. So let V equal volume. So moles per liter, well, we're going to call mole N, and we'll call liter generally a volume, RT. So we just replace capital M with N over V. Let's go ahead and replace, let's cross multiply the V. So we're going to multiply both sides by V. So we have pi V is I nRT. And now you notice that we can probably go ahead and replace the pi with a P. V I nRT. Well, this looks very similar to the ideal gas equation. So this is the ideal gas equation. The only thing is we have this Van 't Hoff factor I. Well, you can have the Van 't Hoff factor here as well, but I is always equal to 1 for gases. So with that fact, they kind of work the same way. So again, when you look at the equation for osmotic pressure, pi, build upon your understanding of ideal gases, PV nRT, because semantically they're connected very closely.